So I'm going to talk today really about two different problems where we've used basically big data, we feel, to make some headway in understanding physics. So the first one is the glass transition. Is this working? No. Okay. The glass transition, where you have molten glass, of course, which behaves like liquid, or you can have solid glass vessels. And the second one has to do with the brain vasculature system and how it works to redirect flow on demand. So, I know why this isn't working, because I didn't turn it on. Okay. I'm a statistical physicist. So my reason for being, as you might say, is to develop microscopic understanding of collective phenomena in many body systems, right? And statistical physics has been incredibly successful over a long period of time. And then basically, what is it doing? It's doing two very important things, many important things, but it comes down to really two things, which is taking very, very detailed microscopic information and boiling it down to just averages or distributions, okay, of a few relevant microscopic quantities. So that's two things. That's doing dimensional reduction, okay, from all this huge amount of information just to the few, and it's providing that bridge from the microscopic to the macroscopic scales through those few relevant variables, which have to be then identified. So, when you talk about what are problems where statistical physics has had a hard time, okay, sort of exhibit A is always the glass transition. So that's where I'm going to start, with exhibit A. So, we've been using glass for a long time. These are vessels from 1500 BC. But that glass transition itself is still, quite a challenge. And when you come down to it, it gets to the heart of what is the difference between a liquid and a solid, right? And so a very simplistic thing is, well, okay, liquids flow and solids don't. That's not quite true, okay? Solids do flow, but very, very slowly, on very long time scales. So what is flow? Well, flow is I apply a stress, okay, and the system relaxes. And that stress relaxes. And it does that in a liquid, but not in a solid. And it takes some time. That time is the relaxation time, okay? And how does it relax that stress? It relaxes that stress by allowing particles to change their neighbors. So in a solid, where every particle is locked into place and doesn't change its neighbors, the stress doesn't relax, okay? But in a liquid, particles are just jiggling around, rearranging all the time. All right, so basically, in the end, the important dynamics are these rearrangements where particles change their neighbors. There's one kind of solid, one class of solids that we understand really well, we've understood them for a long time, and that's crystals, right? The freezing transition. When you go from the liquid to the crystal, the constituent particles, which could be water molecules or whatever you like, they're disordered in the liquid, right? But then they become ordered in the crystal. They develop periodic order. And what happens to the relaxation time then? Well, it's short in the liquid, and then it jumps to become extremely long in the crystal. So that's a discontinuous increase of the relaxation time, okay? And as I said, this is something we've understood for a long, long time. But the glass transition is fundamentally different, right? Because the particles remain in disordered configurations. In fact, if you look at the structure of glass and you look at the structure of liquid, you'd be very hard-pressed to tell the difference, okay? The relaxation time, as you cool the system down, okay, increases continuously, not discontinuously, and very, very rapidly. So you can get a 10 magnitude increase of the relaxation time in just tens of degrees. It's an incredibly dramatic change of the relaxation time. And because it's so dramatic, basically, it rapidly goes out of the window of time that you're willing to spend to measure it. Okay, and once it passes out of that window, we just call it a glass. Okay, but if we waited longer, it's a liquid. So this is a universal phenomenon because every single liquid will do this if you can cool it quickly enough so that little crystallites can't form, can't nucleate. Okay, so if you cool them down quickly enough so you don't worry about competing with crystallization, then they all go through this glass transition. And because it's a universal phenomenon like that, it requires a universal explanation. Yeah?
So just because of the way you explain things, so would you call like supercooled water still liquid glass? It's like you're going slowly enough that you're not nucleating the crystal.
Right, so supercooled water can show features of glassy dynamics. But you don't, it's very hard to supercool it to the point where the time for the system to relax is longer than what you're willing to wait. And so it's not a glass. But it can show hallmarks of glassy dynamics approaching it. Yeah, feel free to just jump in and ask questions, please. Okay, so, right, as I said, the goal of statistical physics. Yeah, what's there?
If you ask questions, hit the button.
Oh, yes, use the microphone, yes. Okay. So as I said, the glass transition, right, is exhibit A for where statistical physics, runs into trouble. And, right, it's lacking important symmetries that often help us. So, for example, the change of symmetry that goes from liquid to the crystal where, you become ordered, that's missing. They're intrinsically far from equilibrium, right? Because a glass is something, by definition, I haven't waited long enough for the system to relax, so it's far from equilibrium. And, it has this complex landscape. So what do I mean by complex landscape, right? You think of a complex landscape, you think of something like this. But this is because we're stuck in our narrow-minded three-dimensional world where we just have a height and two position coordinates. But if you think about the world that the glass is living in, or a glassy liquid, right, I have an energy landscape for a system of n particles, okay? So that energy is a height, but it has now 3n different position coordinates in an n particle system, or dn position coordinates in a d-dimensional system. So that's huge. And not only that, it has of order e to the order n minima. And so that's, if you have only 1,000 particles, not a very large system, you already have of order 10 to the 1,000 minima, okay? So this is a really, really challenging problem to handle, okay? And the interesting thing is that the properties have to be inextricably linked to the dynamics when you're in this landscape, because in order for the system, for particles to rearrange, okay, you have to go from one minimum to another. You have to go over an energy barrier, okay? And that means that the dynamics are tied to that complex energy landscape, okay? And everything is tied to that landscape. So what happens? Well, if it were just a matter of getting over a barrier, okay, then what you would expect is the relaxation time would just be exponential, right, and the energy barrier divided by temperature, just the Boltzmann factor. And that would give you, and that's if I had a well-defined energy barrier, that's what I would see. And if you plotted log, this is viscosity, but equally well, it could be relaxation time. So log of the relaxation time versus 1 over temperature, right, it should be a straight line for a dependence like this. And indeed, there are some glass formers that behave like that, okay? These tend to be things like actually window glass, silica, network glasses tend to be what are called strong glass formers. They have nearly Arrhenius temperature dependencies, okay? But the vast majority of glass formers actually don't behave like that. They have what is called super Arrhenius behavior, so they diverge more rapidly than you would expect given a well-defined energy barrier. And so in some sense, that's as if your energy barrier is getting higher and higher as you lower the temperature. So not only is it your thermal fluctuations and making it harder to get over a barrier, but the barrier is actually getting higher. And that's what gives rise to this incredibly sluggish dynamics and this very rapid rise of the relaxation time with temperature. And then there's still other systems that are actually sub-Arrhenius, where it curves the other way, so that the energy barriers actually get lower as you lower the temperature. Okay, so you can have all these different kinds of behavior. So that's one thing then that's very important, is the temperature dependence of the relaxation time. Okay. Another characteristic of glassy dynamics is the dynamical heterogeneities. And we're all familiar with this, by the way, in a very simple 1D example, which has common physics with this, namely traffic. You know, you get into a jam, right? All of a sudden, people in the next lane are whizzing by and you are stuck. That always happens, right? Whereas if you're far from the jam, that doesn't. Everybody's pretty much moving, covering the same amount of distance in a given interval of time. Okay, so as you get closer and closer to jamming, the distribution of how far each car can go in a given interval of time gets wider and wider. Okay, and that's what happens as you approach the glass transition. This is a simple example from a granular system. This is an experiment where this is plotting the grains, okay, and how far are they moving in a given interval of time. And that interval of time is the relaxation time. And the red ones are the ones that are moving further, whereas the blue ones are pretty much stuck in place. So you can see their tracks during that time. And you can see that there's a lot of heterogeneity in it. And that heterogeneity gets more and more pronounced as you lower the temperature. So that's another thing that you want to understand. So how do you quantify that? Well, you can say, well, how far did I move in a given interval of time? Okay, and if I moved more than some distance A, okay, I'm going to say, if I move less than A, I'm going to say I have a lot of overlap with where I was, and I'm going to define an overlap parameter which is 1 if I moved less than A. But if I moved more than A, okay, then it's 0. Okay, so I can define that for every particle. Okay, and then if you look at the average, that average is going to decay over time, because after a while, everybody's going to have moved, okay? And as you lower the temperature, okay, it takes longer and longer for this thing to decay. That's the relaxation time increasing. As you lower the temperature, it takes longer and longer for the average to decay. But there's also a variance, right? So, as I said, some cars move a lot, whereas others are stuck. And so some particles, you know, Q will drop very rapidly, others it drops very slowly. And so there's not only an average, but a variance to the overlap from particle to particle, okay? And that variance we call chi4, it's a function of time. And what you see is that it has a peak, okay? So this is at a high temperature, it has a peak, and then it decays, okay? And as I lower the temperature, that peak gets bigger and bigger, and it shifts to longer and longer times. And there are two things. First of all, the position of that peak, the time at which that peak occurs, is in fact a measure of that relaxation time. So the variance is biggest on the scale of the relaxation time. Some particles have moved, and other particles have not. Okay, so that's. The other thing is the peak height. Okay, so that, as you can see, gets bigger and bigger as you lower the temperature. And that's why you can see dynamical heterogeneities in traffic when you're close to jamming, because they got bigger, okay? That peak height got bigger. All right, so back to statistical physics, we got this hard problem, okay? And so it's natural to say, what can machine learning do for us? Why? Because why is it natural to ask that? It's because machine learning was designed for dimensional reduction. And that's a lot of what we're doing in statistical physics is dimensional reduction. So it makes sense, right? But the thing is, of course, machine learning was designed for by computer scientists to do computer science things. We want to do physics with it. And so what we need to ask is, there were two things that statistical physics did for us. One was dimensional reduction, but the other thing is to find the right microscopic variables that will give us insight into the problem. Okay, so how can we do that? All right, so let's think a little bit. Let's go back to this thing about the difference between liquids and solids, right? So in ordinary liquids, sort of any particle can rearrange. Any of the constituent particles can rearrange at any time, okay? But what about solids? And so let's think about what we know about crystals first, since we understand crystals so well. So in crystals, not all particles are equal, okay? The ones that are really important and far more likely to rearrange due to thermal fluctuations are particles that are at certain kinds of defects, okay? And so this is a colloidal crystal. And you see, this is what's called a grain boundary. So you have one crystallite grain here, you have another one here, which is has a different orientation, okay? And what you can see is that when you approach the glass, the melting transition, you raise the temperature, it tends to melt. What you see is that the melting occurs preferentially at that grain boundary, okay? So particles at grain boundaries are far, far more likely to rearrange than particles that are well inside the crystalline domains. And why? Well, they have much lower energy barriers in the grain boundaries, okay? So the energy barriers are lower for particles that are in these defects. So that's been a question in the glass literature, the glass transition literature, for over 50 years, okay? Which is, can we identify defects that are like dislocations, okay, in crystals that correlate with their propensity to rearrange? How likely are they to rearrange, and how high their energy barriers are, okay? And people have been, as I said, banging their heads against this for many, many decades, okay? Lots of things proposed. And the usual physics way to do things is, right, you think really hard and say, I think this is the important physics. Or I think that's the important physics. And you try it, and it doesn't work very well. It might convince your mother, okay? So this is where we said, well, okay, this is the kind of thing that machine learning is really good at, okay? So can we find these defects using machine learning? And yes, the answer is yes. And in fact, the simplest and dumbest machine learning methods work extremely well, okay? It's, for a machine learning perspective, this is an incredibly easy problem, okay? And what's the difference, right? In machine learning, you don't try to find just one thing that captures everything you want, okay? You look at a whole bunch of things, and you use that combination of them. So in fact, what we do is we use the pair correlation function. In other words, the density of particles that are at a certain distance away from the particle, okay, at different distances away from the particle. So on average, the pair correlation function looks like this. There's nothing very, very close by to the particle because they're repulsive at short distances. Then they all build up. This is called the first coordination shell. Then there's a dip, and then there's a second neighbors, and so forth. Okay, so that's a typical pair correlation function for a particle in a liquid. And of course, there are fluctuations from particle to particle. Different particles have different structural environments, that they're local structural environments characterized by different, forms of this.
Frequency is constant.
Yes. So this is all at zero frequency.
Well,
But,
between the hills.
the distance between these. Yes, it's pretty much set by the particle size. So you have your particle, and then you have your first layer of particles. So in a dense liquid, it's basically set by the particle diameter. Okay, so they build up outside, and then the next ones build out outside those. Okay.
The hills.
Yes, that's right. And it keeps going for a while in a dense liquid. Okay. That's exactly right. Okay, so what we're going to do is we're going to take a weighted integral. This this is a vector integral, of course, d to the dr in d dimensions. Okay, we're going to take a weighted integral of the individual pair correlation function for particle I with a weighting function. Okay, and the point is that we're going to choose these weights, okay, so that we get the strongest correlation with rearrangements that we can get. Okay, so the weights are the same for every particle. This weighting function is the same for every particle. It's only this that changes from particle to particle. And from that, we get a quantity that we call softness. And this works. Okay, we have a dividing surface where particles that are likely to rearrange are one side have positive softness. Particles that are less likely have negative softness. And 90% of the rearranging particles have positive softness. Okay, and what does this distribution look like? Well, it's actually approximately Gaussian. And from a statistical physics point of view, that makes us really happy. We love Gaussian distributions. Okay, and it is Gaussian. And it has spatial correlations. Okay, so if you look at the spatial correlations of that depends on temperature. This is as a function of temperature, so red is a high temperature. So what you see, by the way, is that distribution shifts to lower softnesses as you cool the system down. Okay, so it becomes less soft. The spatial correlations actually increase extremely slowly as you lower the temperature, and they decay exponentially. It's a nice exponential decay, okay, on the scale of a particle. Okay, so, from the point of view of, a statistical physicist, this looks good. All right? So I said, okay, it does pretty well at predicting rearrangements, and it's a structural quantity. I don't need to know the interactions even between particles, which from an experimental point of view is great, because we often don't know the interactions. So we can just get it from snapshots, just the positions. Okay? So we've applied this to experiments as well as to...
Sorry,
Yeah.
I still don't understand. So, if you sample different GIs, will they have very broad distribution? So will they look roughly the same?
There is quite a distribution, yeah.
And so and you try to find W to maximize the variance, or what?
No, we've tried to find W to get the strongest correlation to rearrangements. So in fact, what we do is we've done many things, okay? But what we end up going back to is the simplest, dumbest way, which is just a support vector machine. So we have a high-dimensional space of, G of R, this thing at every different R. So you discretize, you have many different Rs. You have one axis for every different R, G of R at every different R, right? And so then the local structural environment of a particle is a point in this high-dimensional space. Okay, and then we train it. We have particles that are just about to rearrange and particles that have not rearranged for a long time. And we find the best dividing hyperplane in that high-dimensional space. And the normal to that hyperplane gives us these weights. So that's what we actually do. We've done this with many different machine learning methods, and even a deep neural network doesn't do much better than the support vector machine.
Can you explain why you call this property softness?
What?
Can you explain why do you call it softness?
Why do we call it softness? Well, because it turns out that particles that are much more likely to rearrange have smaller heights of their first peak and higher valleys. Okay? So they have what are called looser cages. So it's sort of their local environment is sort of soft. It allows them to escape. So that's why we called it. It's not a great name. I have to sort of apologize for it, but yeah.
So this might be a silly question, but wouldn't this be related to like the local density of particles? And how much do you gain from using this versus just using the local density?
It is the local density at different values of R.
Okay.
But it's a weighted integral. And what that does is that exaggerates very subtle differences, okay, in a way that's helpful for us. Okay.
You have two types of functions. One is kind of flat, and the other is very cagey, as you say, and you choose the weights to discriminate between
between these, basically. That's right. Okay. So we can do this, right? But so what, right? So what? So first of all, it's a microscopic quantity, okay? And it's relevant to dynamics, okay? And dynamics, rearrangements, as I said, are at the heart of the glass transition, right? And glassy dynamics, because that's how the system relaxes, is through these rearrangements. And so you can ask, is it a structural order parameter for the glass transition? Can it tell us something about, for example, the temperature dependence of the relaxation time and those dynamic heterogeneities? Okay, can we actually use it now to learn something about a collective property? So, and here's the wonderful thing about it, okay? It turns out that if I look at the probability that a particle will rearrange, okay, and I pick out particles of a given softness. So these red ones have a high softness. These blue ones have a low softness, okay? So if I look at particles of a given softness and plot the probability, the log of the probability that they're going to rearrange over 1 over temperature, I get a straight line. And why is that important? Because that's Arrhenius behavior. That's saying that the probability is e to something. There's a well-defined energy barrier for rearrangement. Okay? So if I look at particles just of one softness, I get a well-defined energy barrier. Okay? And I can pull it out, right? So there's an energy barrier that's a function of softness. And that, right, why so great? Because remember, I had this incredibly complex landscape, you know, with all of these minima. And mapping out the barriers in this system is a horrible, horrible problem. Okay, people have done it for of order 50 particles. Okay, but that's already a monumental numerical undertaking to try to do that. Okay, but this gives it to us for free. We can pull out the characteristic energy barrier that a particle of a given softness has to overcome in order to rearrange. Okay, just from this structural measurement. Okay, now this appears to be generally true for every system that we've looked at so far. So it's not only true for, this is a Leonard-Jones mixture, this is a very strongly super-Arrhenius behavior, where energy barrier that rises very rapidly as you cool the system. Here's a model of silica, which is quite Arrhenius, so just seems to be a reasonably well-defined energy barrier. And again, we get this. Here is a system. These are spheres with harmonic repulsions, just spring repulsions, okay, at different packing fractions near the jamming transition going above it. And it turns out that as you change the packing fraction, you change the temperature dependence of the relaxation time, so that it's much stronger if you're near the jamming transition, and it becomes more and more strongly super-Arrhenius as you raise the density. Okay, and so this is a system where we can use the same weights over all different packing fractions and temperatures, so just one set of weights. Okay, and so we can really compare the energy barriers across systems, and again we see this nice Arrhenius behavior. Okay, so we can pull out the energy barriers at a given softness. Okay, so and here's a system that's actually sub-Arrhenius that I mentioned. It's actually a model of epithelial tissue, okay, that shows sub-Arrhenius behavior. And here's a crystal. This is aluminum, okay, but it's not a perfect crystal. It's a polycrystal, and so I had these grain boundaries, right, where particles have lower barriers, and indeed I can pull out, again, the probability of rearranging in these systems too, and it is Arrhenius, well-defined energy barrier. So softness tells us the energy barrier that has to be overcome in order to rearrange. Okay, and it does that across the whole spectrum from sub-Arrhenius to super-Arrhenius behavior, across the spectrum from order to disorder. Okay, and so it gives us the hope that we have then a universal description, right, for this universal phenomenon. All right.
So are those weights universal if you normalize them properly?
The weights are not universal. The weights vary from system to system. For a given system, we can choose a single set of weights over all temperatures. And for that one class of systems, the harmonic repulsive spheres, we're able to use a single set of weights across all densities as well as all temperatures. Okay, but it is a different definition from system to system. So, and that's interesting, right? Because that's very different from a dislocation in a crystal, which has a universal definition, but non-universal emergent behavior that comes out of it. This thing is the opposite. It has a non-universal definition, but then universal behavior that emerges from it. Okay. All right. So, and what do we want to now? We've got this quantity. We want to build a theory with it. Okay. That's the point. We're not just trying to predict rearrangements. Who cares about that, right? We're trying to build a theory. We're trying to understand what's happening. And so what we want to describe, right, is this overlap function and you know, the variance of it, the peak height, you know, how heterogeneous are the dynamics and what's the relaxation time, which is the peak position. Okay, that's what we want to capture with the theory. So the simplest, dumbest theory that you could write down, okay, is just to say, well, we're going to let particles rearrange with a probability that we've measured. It's Arrhenius. We know the energy barrier. Okay, so we know that probability of rearranging. And we're just going to let them do that totally independently. And every time a particle rearranges, we're going to just draw a new softness from this underlying distribution. Okay, this is called a trap model. It was introduced by Jean-Philippe Bouchot for glasses many years ago. And so we're just going to do that. And whenever this thing rearranges, it's totally uncorrelated with what the other particles are doing. Okay, simplest, dumbest model. So what does it give you? Well, here are the simulations, and here is the theory. And so for the average softness, it's actually terrible. This is really a big difference on the scale compared to the variance. Okay, so it doesn't do well on predicting the average softness. The relaxation time, the dependence on temperature is actually surprisingly not so bad. But if you look at that, the peak height, remember I said the heterogeneities get bigger and bigger as you lower the temperature, more and more pronounced. So the peak height increases. That's the height of that peak, the variance of the overlap. In this model, it's totally flat. Okay, so it really just completely falls down on this. So now you can say, all right, it's missing something really important. Okay, what is it? What is missing? And the answer is correlations, right? We totally left out all the correlations. So now we can start putting them back in. All right, so how do we do that? Well, here's the thing, right? The structure, we have the structure, and it's quantified by softness. The local structural environment of every particle is quantified by its softness, right? By that weighted integral of the pair correlation function. All right, so the softness determines what is the probability that a particle will rearrange. But suppose the particle rearranges. That scrambles the structure, okay, of that particle, around that, of the neighborhood around that particle, but it also scrambles the structure of spectator particles that are nearby. Okay, their local structural environment is affected. So not only its softness changes, but nearby particles, their softness will change too. And that's that interplay. And once their softness changes, well, that can, okay, that's this part, that can change then whether or not they rearrange. And that's the kind of correlation that turns out to be incredibly important, okay? Because we can now sort of put in these correlations one at a time. All right, so that's what we need to capture is that interplay. And that comes about because when there's a rearrangement, I change the softness, not only of my particle, but the particles nearby. But that change, if we're going to build a model, we have to recognize that our system is locally in thermal equilibrium. okay? Which means that it has to obey detailed balance and time reversal symmetry. So if I run the rearrangement forwards and backwards, I have to get the same thing, right? The change of softness that I get has to be consistent with being in thermal equilibrium. And so that puts severe constraints actually on the kinds of, on the model, okay? And it makes it possible to actually do it. So I'm not going to go into the details. I'm just going to say that there are two key things, that the distribution of softness is essentially Gaussian, okay? And we assume that the distribution of softness, the change of softness, is also Gaussian. It turns out that that's also a very good approximation. And we can find that it has a certain form, okay, the change of softness, which depends on the distance from the particle. And from detailed balance, we get sort of constraints on what these things can be. All right, I'm not going to go into details. But the key is how far away, how does the softness of a particle here depend on whether I had a rearrangement over here? It turns out that decays exponentially on the scale of the softness correlation itself, okay? And so we feel that we're really understanding something here. The fact that it's a nice, simple exponential makes us think, okay, we're on the right track, okay? And so what comes out of the model? Well, we do much better with the average softness, okay? It's now agreeing quite well within the standard deviation. We get this growth of the dynamic heterogeneity as we cool down the system. They become more and more pronounced and moves to later times. So the relaxation time does quite well. This is the theory, that's the simulation. The peak height, again, does quite well. And we have correlations, a correlation length that for this. In other words, how is the variance, the overlap here correlated with the overlap over there, okay? So if this particle is likely to rearrange, how likely is this to rearrange? Those correlations, that correlation length grows as you lower the temperature, okay? And we capture that quite well. There's an overall prefactor, and this is because to solve the model, we're putting it on a lattice, and we haven't worried about what that lattice constant should be. We've just taken it to be a particle, okay? But that affects that length scale a lot, okay? All right, so the point is we've got a model that does better, and what do we have to put into it in order to get it to work better? That tells us what's important, right? The two things was that facilitation, the fact that if I rearrange, I'm going to affect the softness of my neighbors. And the other thing was the spatial correlations of softness that had to be also put in. Okay, and these two things are necessary in order to get this kind of behavior. Okay, so we've learned something about the correlations. Okay, so why was machine learning so useful here? Okay, well, first of all, as I said, it was designed for dimensional reduction. But the other thing about it, right, this is what machine learning is great at. It's great at finding subtle correlations, okay, that usual physics approaches that try to just look at one key thing that captures everything, okay, one ring to rule them all, whatever, just can't get, okay? So we think there's just a lot of possibility for using machine learning to identify, order parameters or important things like this in systems where the correlations are very subtle. Okay, so that was one problem. Now I want to go to another problem. I'm going to switch gears to a second problem where we feel that we've made progress again using big data ideas. Okay, and that is a living matter problem. Okay. And the problem with living matter, and this is a picture of the brain vascular system, okay, which I'll tell you more about. It's the system of blood vessels in our brains. The problem with living matter is that on top of, being far from equilibrium, lacking symmetries, and often having complex landscapes, all the problems that were a problem for the glass problem, okay, it's even worse because they're not even disordered. Okay? In other words, the vascular system has a certain sort of structure in it, and that structure is not random. It's not as if the widths of blood vessels, the diameters of blood vessels here are chosen randomly. They're not chosen randomly, okay? And that's very important for enabling them to do what they can do. So these are systems where every constituent can be different, okay? In statistical physics, we like to have most our constituents all to be the same, right? Or at least a few classes of them. Maybe I have different components, okay? Different kinds of components, but not too many. We don't want everybody to be different. That's very, very hard to handle, okay? But that can happen, and they are different for a reason, okay? And that difference is actually important to their function, okay? The other problem with living matter, so these are huge problems for statistical physics, okay? But if I now think about using big data, I have a problem because I don't have big data. I have tiny data, okay? So we know from statistical physics, right, that we need ensembles. When we're trying to find a signal in a system with a lot of noise, with a lot of variation, we need large ensembles. But here we need evolved or trained ensembles, and we don't have such ensembles. So let me talk about the brain vascular system as an example of that. So I learned about this system from my wonderful colleague, Eleni Catafori. So the brain, right, is actually only 2% of the body mass, but it uses nearly 25% of the oxygen that comes into our lungs. Okay, and what it's doing, right, is it's taking, right now I'm talking, right, so I need extra oxygen at my speech cortex. And my brain vascular system is directing extra blood flow to my speech cortex. Now, if I stop talking and started jumping up and down, you'd think I was a crazy person, but my brain would make that adjustment and send extra blood flow to a different place, right? And so how does it do that? It's doing that in real time. And what it's doing is vessels, individual vessels are contracting, some are contracting, others are dilating in order to deliver that blood flow to the right place. Okay, so blood is coming in through the arteries. So there's a source, pressure drop across this system, or source current coming in through the arteries. And now I want to deliver a specific pressure drop or current, okay, to a certain target that's far away from the arteries. It's elsewhere in the vascular system. And we call that flow allostery. Allostery means it's happening somewhere else. And you've got the input at the source, and the target is somewhere else, okay? It's a localized response to a localized perturbation that's where the two are far apart from each other, okay? So how does the brain vascular system manage to do this? What's it doing, okay? So, all right, so people are starting to map out these vascular networks for different mice, okay, different individual mice, okay, David Kleinfeld. Beautiful data, but it's not in real time. He can't say, oh, this vessel is dilating and this one's contracting, right, in real time. That's impossible to map out. And these are very small ensembles. Okay, so this is not big enough data to use big data. So what do? So what we do is we design our own flow networks that have this property. And then we can have as many as we want, okay? And then we can say, what do they have in common? So how do we design them? Well, we take a leaf from machine learning, of course. All right, so what do you do when you're tuning a deep neural network? Well, you introduce some cost function, which in this case is the pressure drop at my target bigger or smaller than the one I want? I want a pressure drop that's at least delta, let's say, in response to a source pressure drop that I'm going to call 1. I want a target pressure drop that's at least delta, okay? So I define a cost function that penalizes me if my pressure drop is smaller than delta, okay? And what do? I minimize this cost function with respect to degrees of freedom, which are the conductances of the edges. So I allow the diameters to shrink or increase to change their conductances, okay? And then you just do gradient descent to minimize this cost function, okay? Just the way you would tune a deep neural network. All right, and so now I can tune this network to have outflow allostery. And this just shows that it works. Here's the pressure drop across the source. I'm going to call that 1. And here's the initial pressure drop across the target. It's 3 orders of magnitude smaller. But now as I start adjusting the conductances of my edges, okay, the target pressure drop increases and increases, okay, until eventually it gets to my what I wanted, which was 0.2 in this case. Okay, there, it got to 0.2. All right, so we can do this. It works very well. So now we have designed ensembles. We can have thousands of these networks in 2 dimensions and 3 dimensions, okay, that have flow allostery. So now what do we want to know? What question are we trying to ask? So, well, we want to know, how does that edge tuning at the microscopic scale, I'm tuning these conductances at the microscopic scale, how does that lead to this flow allosteric function at the collective scale? Well, when you don't know what to do, you always look at extreme cases, right? So let's look in a flow network. If I put a pressure drop of 1 here at the source, the largest pressure drop I can possibly get anywhere is 1. That's the limit, okay? And so if I tune the target pressure drop to be 1, okay, here are 2 different networks. This is with periodic boundary conditions, okay? What you see is that something very interesting happens. It divides into 2 pieces where all the node pressures here are minus 0.5 and all the node pressures out here are plus 0.5, okay? And I've removed all of these edges here. I've effectively removed them so that my source and my target nodes, my 2 target nodes span between these 2 sectors, okay? And here's another case, okay? And what you see here is that what has changed is a topological thing, okay? I went from having 1 network to having 2 pieces, 2 networks. They're essentially detached from each other except at the source and target, okay? So, and it doesn't matter, right, what the shape of that boundary is. As long as I divide into 2 sectors, I'm fine. So because I can count it, it's topological. And so then we say, all right, that's the extreme case. But suppose I didn't want to tune to the extreme case. I just showed you an example where we'd tune to delta of 0.2, okay, a response that's 20% of the source. Then it's not going to break up into 2 networks. It's just still 1 network. But the fact that we see this topological change in the extreme case led us to say, well, maybe we should try persistent homology, okay? So we did, and that works beautifully, okay? I'm not going to tell you how it works. I'm just going to say that from the persistent homology analysis, we can pull out these 2 sectors, okay? And so this is the extreme case. I have this sector and I have that sector, and all the node pressures are minus 0.5 in the orange sector, and they're all plus 0.5 in the green sector. And if I take the average of this distribution and the average of that distribution and subtract, I get the pressure drop that was tuned in. The sectors tell me everything, okay? Here's a less extreme case, this is tuning to 0.2. In fact, that was just the minimum, and we ended up tuning to about 0.27, okay? And I can look, again, from persistent homology, I can extract these sectors, okay, connected components, and the average in the green, and I can look at the average of the orange, and that's 0.29, extremely close to what I tuned in, okay? Here, this is only 0.05, okay, a response of only 0.05. I now look at the distributions. They're actually even overlapping now, but if I look at the mean, okay, it's 0.14. In this case, what came out was 0.17. Okay, the actual pressure drop that we tuned in was quite overshot the desired goal and was 0.17. And this, again, gave us something very close, okay? And if I have one source and many targets, okay, what I see is that the system breaks into several sectors, and I can find these sectors again. Again, several sectors of nearly uniform node pressure with my different target nodes spanning boundaries of these sectors, okay? So this is a huge simplification. This is dimensional reduction, right? I've gone from needing to know everything about this network to just needing to know, oh, there's sectors, okay? And all I need to know, in fact, is the average node pressure within each sector, and I can reproduce the actual tune difference. So this is just, the dashed line here corresponds to the average node pressure in the sectors telling us what the tune pressure drop is versus the actual tune pressure drop. And you see it's very close to the straight line, which is them being equal. And this is true for one target for different size systems, or for one size system with varying numbers of targets. And you notice that in a system with 512 nodes, we can easily tune even 128 different allosteric sites, which is good news for those of us who like to multitask. Okay, all right. Okay, so the message here is that how does edge tuning lead to that allosteric function? Well, it affects the topological structure of the response, and we're incredibly lucky that the most topologically significant features, which are these sectors, actually tell us what the function is quantitatively. Okay, so what are the implications of this? Just first for the brain vasculature. Well, so far the emphasis has been totally on the network topology. It's like the version of the connectome. But that's not enough, right? This depends very sensitively on the diameters of all the vessels, okay? And those are changing in real time, okay? So, and if you want to know the network topology, you really have to have each edge specified completely. But what we're saying is, no, really you should focus on the node pressures. If there was some way to think about ways to measure the node pressure, or the pressure drop across each edge. And then even incomplete data could still be very helpful in defining these sectors and identifying these sectors, because within a sector, the node pressures are nearly equal, okay? And of course, this appears in lots of different kinds of networks, and so it's a question, is persistent homology useful in actually, for example, figuring out what a neural network has learned? All right. So just to wrap up then, I showed you that this statistical physics big data approach, right? We first had to provide the big data, so we designed ensembles. But then we had ensembles that all had the same function, so we could look at what they had in common. We found it was topological, okay? And that persistent homology did the dimensional reduction for us, right? Because it took all that information and said, all you need to know is the average node pressure in each sector. Okay, so a lot of people, when we first started doing machine learning, a lot of people said, I don't want the machine to learn for me. I want to learn something, okay? And just saying, don't worry. Machine learning can help you do that, okay? They're natural because they're designed for dimensional reduction. But luckily, we, the learners, have not been replaced by machines. Okay, we're still necessary because physical insight is really needed to ask the right questions, to know which questions a data science can help with and which cannot. Designing the right ensembles, that's very key, right? Choosing the appropriate data science approach, which, in the second case was persistent homology, okay? And identifying the relevant microscopic variables. There's a ton of physics to be done here. And I just think there's so much promise in these methods once we learn how to harness them to our own goals. So just to thank the people who did the work. This is on the softness and classy dynamics. And this is on the second part on allostery and persistent homology. And thanks very much for your attention.